Benjamin Böhm from Friedrich Schiller University of Jena, and talking about CDCL versus resolution in QBF.
Yeah, thanks very much. So this is based on joint work with Olaf Beiersdorf from Jena in Germany, not to be confused with Vienna in Austria, and Thomas Speidel from Jena in Austria. We already heard a talk today about QBF, where we have seen what is the connection between QBF and circuit complexity, and now we're interested in well, QBF solving in terms of QCDCL and QBF proof systems that are based on resolution. So luckily, I don't have to explain too much about QBF because we already heard that. So let's just make a quick reminder for you. So we are dealing with quantified Boolean formulas. Each formula consists of a prefix that are all quantifiers and a matrix that is just a propositional formula in CNF. And we want to find out if our formula is false or true. And if it is false, we want to return a refutation. And if it is true, we want to get a the opposite of a refutation, I would say, is a verification. Okay, so we also heard about QBF proof systems before, but I think we only defined QU resolution. So let me start with Q resolution because this is naturally the first one you would define. But first, let me say that in our settings, I said here, we want refutation or verification. In our setting, we will only concentrate on false formulas and refutations because verifications work a little bit differently and are a little bit more complicated. So for our setting here, where we want to find separations and lower bounds and so on, it's enough to only consider false formulas. But keep in mind that our formulas might also be true in general. Okay, and for our work here, we consider 3 refutation proof systems. The first one, Q resolution, or short QRes, which was introduced in the 90s by Kleine-Bühning, Kapinski, and Flögel. This is just, as you know, the extension of propositional resolution. And you have already seen this resolution rule. I don't have to explain this here. However, here in Q resolution, we have this slight restriction that the X, our pivot, has to be existential, and C or G should be non-tautological. And we have this reduction rule, as you've already seen, that we can just get rid of the U if there are no existential literals right of U in this clause C or U. And as you already know this, I would say refutation is just a derivation of the empty clause. So we want to get the empty clause somehow. And there are 2 more systems, or even 3, but we only consider the first 2 systems. The first one here is long distance Q resolution, or short LDQRes, introduced in 2002 by Zhang and Malik. Now I won't explain this in detail how this is defined because it would take too much time. Just let you know that it is basically like Q resolution, but it allows some certain resolution steps that were forbidden before. But for this talk, it's not crucially important to know what these extra rules are. And yeah, you've already seen QU resolution introduced by Gelder 2012, which is just Q resolution, but we are also allowed to resolve over universal literals. And you can also combine these 2 systems into this long distance QU plus resolution, or LDQU plus res. 2014. Okay, now you've seen how our refutations might look like. Here's the simulation order of these resolution-based QBF systems. So the weakest one is this QRes. It's pretty natural to see that that's the weakest one, and then LDQRes and QURes are, I'm not sure if it's correct to say they are equally strong, but they're incomparable, but they're both stronger than QRes, and the strongest one is this LDQU plus res. Now you know how your refutations might look like. On a question, how can we obtain such a refutation? And luckily, in the first talk today, we also heard about CDCL, And we can just lift CDCL to QCDCL, which is the QBF case for CDCL, which is one of the main, not the only one, but one of the main paradigms for QBF solving. And I've created this little picture here. So QCDCL works similar to CDCL, but there are some slight differences. So maybe let's see, you start up here, you have your QBF or QCNF, QBF and CNF. You check if at the beginning, if it is falsified or satisfied. So here you check if your matrix is falsified or satisfied. Naturally, this should not be the case at the beginning, but it will be important in later runs. So let's say it's not falsified and not satisfied. So we check if there are unit clauses or unit terms. So that's now new, that you also check for unit terms, because you need terms for QBFs. So a term is just the opposite of a clause. And if there are any unit clauses or terms, you do unit propagation, and if not, you make a decision, and then you go up here again and check again. And at some point, you will either falsify or satisfy your matrix. If you falsify it, you just learn a clause like you know from CDCL. If it is the empty clause, then you're done because your QBF is now false. If it's not empty, then you can learn this clause, you can add it to your matrix and backtrack and start all over again. Some crucial difference in QCDCL is that if your matrix gets satisfied, then it doesn't mean that the whole formula was true, because it might be the case that there are false QBFs where you can satisfy the matrix, but they are false because of the quantifiers. So when we satisfy the matrix at some point, we instead learn a term, and only if this term is empty, then it is true. Otherwise, we also add this term and do backtracking. But again, we only concentrate on false formulas, so this left side here is a little bit more important for us. Now, what do we know about the connections between QCDCL and resolution-based systems so far? So as I think many of you know, that DPLL corresponds to tree-like resolution, because here you get these decision trees, and if you flip them, you exactly get tree-like resolution proofs. Then in the SAT case and CDCL, from CDCL, you also have seen that you can extract resolution refutations. But a surprising result from 2011 showed that the other direction is also true. So you can basically extract CDCL runs out of a given resolution proof. That's pretty crazy, I would say. So therefore, you could say that CDCL, if you interpret it as a proof system, is equivalent to resolution. And now we simply ask the question for the QBF case. Yeah, what is the connection between QCDCL, Q resolution, or QCDCL and LDQ resolution? The only thing we know so far is that we can extract LDQ-res proofs out of QCDCL, because that was the whole purpose of defining LDQ-res to formalize QCDCL a little bit. Okay, so here you can see at which point in this whole graphic, this whole algorithm, we can extract these proofs. This is exactly here when we learn a clause. There we can, you already know that in CDCL you can extract resolution proofs, and here you extract LDQ-res derivations of these learned clauses. And at the end you have the empty clause, and therefore you get the derivation of the empty clause, and you can stick together all these derivations and get one big refutation of your complete formula. Now, what can we say about QCDCL versus resolution? Come back to this question. Now, that was the first result of our paper from 2021, and we've shown that actually QCDCL, the classic QCDCL as we know it, and Q resolution are incomparable as proof systems. That means there exists separations in both directions. However, we can slightly modify this QCDCL, which I will explain later a little bit more in detail. And then this modified version of QCDCL is equivalent to Q resolution. Now, if you think about it, so I said that you can extract LD-QRes proofs out of QCDCL, and LD-QRes is a stronger proof system than QRes, but QCDCL cannot even simulate QRes itself, which is the weaker one. So why is this the case? What is the weakness of this classical non-modified QCDCL? Why does it not work to simulate Q resolution? Now, I have not the time to explain this in detail, but this was also from 2021 from our SAT paper. We have shown that there exists a lower bound technique, so not only one lower bound, but a whole technique of classical QCDCL, at least for a particular class of formulas. Like I said, I won't explain this here, but the thing you should, or I should point out, is that this technique exploits the fact that decisions need to follow quantification order. I think this is something I haven't taught before. So when you make a decision in the classical setting, these decision sets have to follow the quantification order. That is what is done in practice. And well, this gives us this weakness for Q resolution. How can we modify QCDCL to make it equivalent or as strong as Q resolution, long distance Q resolution, and so on? So our purpose is to find out if QCDCL can theoretically, as a proof system, reach the strength of these proof systems I have defined before. And for this, we applied 3 kinds of so-called policies, which are just these modifications to QCDCL. So these are decision policies, reduction policies, and propagation policies. I will go through all these, explain them, how they work and where they work. Let's start with decision policies. Now, this happens here, of course. This is the only point where we make decisions right after not finding any unit clauses. We have to make a decision. And like I said, in the classical setting, we have to follow the quantification order. However, this is not good because of our lower bound technique. So our idea is just to allow arbitrary decisions that do not follow quantification order. It's as easy as it sounds. So now we have these 2 policies. The first one, lev ord, which is just level order decisions, or decisions that follow the quantification order, and the other one, any ord. You can use any order as decisions. And then from our original proof system QCDCL or algorithm, we get 2. The first one, QCDCL lev ord, which is just our classical, but we just call it QCDCL lev ord now to see policy is included, and the other one, QCDCL any ord. Now, unfortunately, this is not enough to simulate Q resolution proofs. What we also have to do is we have to change the way we reduce literals. And we here are looking at reductions during unit propagation. So of course, there are other points where reduction can be applied. For example, here when we learn a clause, and of course, when we learn clauses, we also reduce universally. But here we only care for reduction during unit propagation. So for this, I should explain how unit propagation in QCDCL works. So you've already seen how it works in CDCL, just classic. You have a clause, and if you falsify all literals except for one, then you have to set this one remaining literal to true, and this is the unit propagation. In QCDCL, it's a little bit different, but similar. So if a clause becomes unit under the current assignment you made, in your trail in QCDCL, and after reduction, universal reduction, then you have to satisfy this clause. So for example, let's consider this clause here, X or U or Y, and your prefix is, let's say, X is X, for U, X is Y, and you just have assigned Y to 0. Then if you apply this assignment to C, then you get this X or U. This is not particularly a unit clause, but a QCDCL, it works as a unit clause because you can simply reduce this U because nothing is right of U. Yeah, so therefore you have to set X to 1 in the setting here. So this is how unit propagation works in QCDCL compared to CDCL. However, there's a little downside with these reductions during unit propagations, because all these reductions are kind of uncontrollable if you want to simulate Q resolution with it, because they all pile up during the clause learning, all literals. You reduce during unit propagations, come back again when you learn a clause, and they can prevent further resolution steps. That's not good. Therefore, we just forbid reductions at all and define these two policies that affect these reductions during unit propagations. So here, the first one is just a classic one, all red. That means always use universal reduction in unit propagation. And the next one, no red, just use plain unit propagation as in CDCL. So now we again double the number of our QCDCL variants we have defined, and now we get 4 of them for each combination once. Again, the leftmost here is the classic one where we started with, and this is the most modified one. Now we can make this interesting result here. If we take this one here with any or, that means arbitrary decisions, and no reductions during unit propagation, we can show that this particular variant of QCDCL as a proof system is equivalent to Q resolution. So now we have succeeded to reach the strength of Q resolution via at least some modified version of QCDCL. Well, that's pretty nice, but we've seen at the beginning the Q resolution is the weakest of these systems, so why not go further? Maybe we can extend it to long distance Q resolution. So how do we gain the strength of long distance Q resolution? For this, we have, again, go back to the reductions, and for LD QRes proofs, we need at least some reductions during unit propagations, but they still need to be controllable. The idea is that we just choose which literals are to be reduced and which not. That means sometimes we can reduce, sometimes not. This is what this new policy, this new reduction policy, any red means. That means we get 2 additional systems here with this any red reduction policy. And with that, unfortunately, we cannot. It's not enough to modify to simulate long distance QRes proofs, because we have to modify long distance itself. I cannot explain this here in detail because this would take too much time, but just trust me that you need to modify also these long distance proofs a little bit. And for this, we define this new model here, this new system, modified LD QRes or MLD QRes. And an important result here is that this is not just defined on the fly because we just wanted it. But all previously defined QCDCL variants, that means all of these, and including the classical QCDCL, are still p-simulated by this MLD QRes. Okay, so basically, you do not actually need this LD QRes anymore. You can just take this modified version, which is a slightly restricted version of that. And then we can get to the next result. And if we take this QCDCL with arbitrary decisions and arbitrary reductions, this model is able to simulate these MLD-QRES resolution proofs. Therefore, it's equivalent as a proof system to this MLD-QRES. Okay. Are there any questions so far? I don't know how much time I have left.
7 minutes.
Okay. Okay, so what we have seen so far, we have characterized tree-like resolution via DPLL. We have characterized resolution via CDCL. This was already known. We could not characterize Q resolution with the classic QCDCL, but with a modified version of that. And we could even do this for this modified long distance QRES. And now the remaining system we want to look at is QURES. And for this, we have to look at the last kind of policy, of modification policies for QCDCL, which are propagation policy. Now we also we already looked at propagation, but now we want to change the propagation itself. So our aim is to find a QCDCL model that characterizes QURES. So in QURES, we are not only allowed to resolve over existential variables, but also over universal ones. So what we have to do here, we have to allow unit propagations also of universal literals. This was, by the way, inspired by a work by Friedrich Slivovsky last year. And he also implemented this. So now we get two more policies. The first one, which we call exiprop, which means that unit propagations, at least via clauses, are only allowed for existential variables, and all prop, which means that unit propagation can be done for existential and universal variables. We again double the amount of QCDCL variants, but I have to say that okay, we have 12 of them now, but not all of them make sense and not all of them are interesting, so we can ignore some of them. So for example, it doesn't make sense to combine all reduction and all propagation, so all red and all prop, because you cannot propagate universal literals and reduce them at the same time. Okay, so from these 12 systems, we look at this one, and we finally come to the last main result here, which says that this variant with any reduction, so with arbitrary decisions, no reductions, and potentially universal propagations is equivalent to QU resolution. So we've also characterized QU resolution now. Okay. Almost the last slide. So this is another overview of all the, I would say, interesting systems we have looked at. I haven't talked about every connection here, but these are all included in our papers. Just to point out, this one here is the one that characterizes this MLD QRES. This one characterizes QRES. This is the classic QCDCL. And what I also want to point out is that from all of these, you see many QCDCL variants here, and from all of these variants, only one variant is really used in practice, and it's implemented. This is that one. You see, it's there's lots of stuff which could be better variants, but yeah. And therefore, I want to end my talk with appealing to all the practitioners out there who work in QBF, and say them that perhaps the most popular algorithm is not always the best one. Thanks.
Thank you. Question? So I have a question. Are there specific, I mean, you mentioned what people have done in actual, in implementations.
Mhm.
Are there particular pieces? You've got 3 different components and slight variance in each aspect. Are there particular components that you think are going to likely be the most productive in terms of adding to what people have implemented?
Well, what we, at least in an experimental setting, tried to implement, so Thomas did this, was this any order. And we found out that actually on these formulas for which we use for the separation, it turned out that you really see these separations also in experiments. And there was at least one, so we have different version of that, but there was at least one variant of this any order that also was better even on benchmark formulas than the classic QCDCL. So yeah, I would say that at least these arbitrary decision orders might be really a good idea, because we really see that otherwise we have this lower bound technique, and the other ones are not so clear. So for example, I mean, when we say any reduction, so you can choose when to reduce and when not. It's not clear how you choose that in practice. But yeah, at some point you should think about this, because in theory, that's better.
So doesn't the same also arise with any order, but there is some non-determinism to how to choose the next decision?
Yeah, right. That's why we tried different versions of any order. So we also tried some restricted versions of any order, where it's not really any order, but
some heuristic is guiding the dictating the order.
But it's more liberal than the order. That's important.
So you said that from these QCDCL runs you can extract LDQRS proofs. That's the original. So those runs do not use term learning, right?
No, we only concentrate on we only concentrate on clause learning. But so when your formula was false, you might have learned some terms, but you can ignore them, because if it turned out to be false, you never use these terms in your refutation. So they're still there. You have learned them during your algorithm, but during your runs, but
they don't shorten the reputations.
They do.
They shorten the trails.
Well, learning terms is important. It can also help it can be helpful for false formulas as well, but they don't turn up in the refutation as well.
So even if the algorithm is running on a false formula and is learning terms along the way, you can still extract an LDQRS. Is that what you're saying?
Yes.
I see.
Yes.
Okay, I did not realize that.
Questions? Okay, let's thank Benjamin again.